Hi, hello everyone. I'm Zhang from Ant Group. Today I will talk about the FLAIR, the Anomaly Diagnostic system we built and deployed in our cluster for LLM training at sound plus GPU scale. This is joint work with our collaborators from the Shanghai Jiao University and the NUS. Today I really want to share a story. That is not only about how we develop and deploy a lightweight cluster-wide tracing system, but more about how we catch and fix the silent slowdown problems that normally will eat in weeks of engineering time. And we have these problems for a long time. Okay, let's dive in. So let me start with why we bothered to building this at the first place, since there are already a lot of similar work. So the first stack of the modern LLM training consists of 3 layers. At the top, it is models, and we have algorithm teams to develop various of algorithms. In the middle, it's infrastructure, and the infrastructure teams ship the parallel backends, kernel libraries, and the frameworks. At the bottom, there are operating system, interconnect, and the GPUs. And we have the operation teams, which are responsible to keep the hardware alive. So if you want to training a LLM at sound GPU scale, you need support from all those teams. So it means at the same time, when something goes wrong, you have to gather engineers from all those teams before you actually figure out the root cause. Unfortunately, so we found most of the engineers are irrelevant to those errors. So our initial motivation is simple and direct. So we want to, in the future, when we have this, have to debug the problems of the training. So we hope to start with less than 5 engineers instead of more than 15 engineers. This table shows our observation on our 6,000 GPU clusters during 3 months. So we have grouped all those abnormal jobs out of around 3,000 total jobs into 3 classes. So there are 127 error jobs that are observed, hung or crash. There are another 57 jobs that run into sudden throughput drop. So actually, those 2 anomaly classes are accurate and well studied and covered by most of the existing providing system. So, but the last one, regression, we can only observe the persistent, subtle slowdown, and it is hard to trigger any immediate alert and just quietly burn your GPU hours. So we found the existing diagnostic systems fail to cover the last one, regression, very well. And now let's talk about our landscape. So we found if you want to solve the regression problems, we need the full stack tracing full stack tracing. So meanwhile, our algorithm teams are using various of backends like Megatron, FSDP, and so on. So then the new system should have 3 important features here. At first, it should be full stack tracing. Second, it must be backend-extensible. And the last one, the most important, automated regression diagnosis. So let's look at what we have now. So max scale, I think it's excellent scale. Excellent system. It's full stack and low overhead. But unfortunately, it works Megatron very well. If you want to extend to some other backends, you have to have some contribute some efforts here. So the rest of one, like a C4D, Greenhound, they are not the full stack tracing, so they can't solve the regression problem. Next, let's talk about what makes building this hard. So we have 2 specific challenges here. So at first, the regression needs to track the full stack of the LLM training that have to connect runtime data across the Python, C++, CUDA, and then CCL. So it means you have to instrument all those runtime. So meanwhile, the algorithm teams are using various of backends in LLM training like Megatron, FSDP, and DeepSpeed. And it is quite possible to have some new one in the near future. So you see, this demands the minimum changes to each backend. Now you can see the clearly conflict between them. So for example, the max scale I have mentioned for several times. So it covers Megatron very well, but you want to extend to the FSDP DeepSpeed, you have to patch this backends by yourself. Okay, let's talk about the second challenges. So for any error, you need to detect it at first, then try to narrow down the root cause. Unfortunately, both parts are non-trivial for the regression. So regression are persistent subtle slowdown and is hard to trigger any immediate warning. So always algorithms just assume their jobs run well. They don't aware of any problems. At the same time, multi teams don't see any red flag. So even you have catch a regression, linking it to some code change is non-trivial. For example, if a Python runtime just kick off a garbage connection on the critical training path, it will impact the training performance. But otherwise, it is harmless. So therefore, we cannot only rely on some traditional metrics to detect and fix the regression problem. We need something new. Now let me work through the design of FLAIR and how it takes those two challenges. FLAIRs include two major components here. So the tracing domain sits on every training processes, one per GPU, and pulls full stack runtime data like a Python API calls, C++ kernel launches timing, code stack, and input layouts. The diagnostic engine aggregate all those data across a job and conduct analysis. So after the engine completes the analysis, it will route different types of anomalies to responsible teams for further processing. So for example, you can see for the errors and phase low will go to operation teams. So regressions will go to algorithm and infrastructure initially. So here pay attention. So FLAIR will not automatically fix those errors. He just tell the engineers what is the possible root cause. He will reduce a lot of time to approach the root cause. So now let's go some details. So let's talk about how the tracer work. So fortunately, we have found that LLM trainings is dominated by a handful of APIs. So in this case, we only have to catch the execution of those APIs to connect the required metrics. No need to patch different backends here. So at first, we'll talk about the Python APIs. So instead of wrapping them with decorators, which means touching every backend, we use the C Python's built-in profiling hook, which is called PY evaluation set profiler, to intercept specific APIs at the bytecode level. So this is how we catch the garbage connection and the data loader and the GPU sync calls. So with no change to the Megatron or FSDP or DeepSpeak. So if you want to trace new APIs, very simple. Just set an environment variable like a trace Python API equal to the names of the function. C++ is simpler, so we just use some traditional method here. We use ALD proload, a classical Linux trick to hook dynamically linked functions. Now let's see. Okay, you can see we just hook some basic some APIs. Not touch the backend at all. So it means we have one tracer works across all the Megatron, FSDP, DeepSpeed, and Torch rank. Even some new backends come, have some new APIs. We just need to update our tracer. We need to change the backend directly. Next, I will introduce how to connect runtime metrics like timing. So I think it's one of the most important metrics. So the Python API is quite simple because it's a sync. So we just need to keep the start and end timestamp directly when it is called. However, a GPU kernels is a different story. They are async here. So for GPU kernels, we just include the cooldown events of at the interception time, one before, one after. So and also we have a background thread which pulls those events to figure out when it actually complete on the GPUs. So the training speed is never blocked. So blocked. This is how we keep the overhead down to less than 0.5%. We will show in the evaluation. Okay, but we still have another problems. Now we have traced the Python and the C++ runtime, but the Python and C++ are traced by different mechanisms. We have to reconstruct it after fact. So here we are using the overlap between the Python and the C++ timestamps. So if a Python API is active from T1 to T2, we just check if a C++ kernel fires inside this window. If it's the case, we link them directly, and now we have the completely the core chain. Okay, now we have the complete the design of the flare and some details. Now let's look at how we solve some important and challenge errors here. So first, let's look at the hang error. So normally there are two major types of hang errors. First one we call it a long communication error. So if a GPU dies or the OS crashes, so the rank is stuck at a long communication core stack, while everyone else will wait on the communication kernel. So then in this case, we just simply check the stack of each rank. Then the fall behind rank is the 41. But if the hang is inside the communication kernel, say link died in the middle of the all reduce, every core stack is identical. All stacks all stuck in the all reduce. So in this case, there is standard fix. So this means we just keep the job and run the NCSL test across all the pairs. But at the 1,000 GPU scale, this will take over 30 minutes of the blind search. So, but we have better solutions. Here, we use CUDA GDP to read the ring steps register of each training process directly from the SAS. So in this figure, you can see the step of the rank 0 is 14, while the other rank is 16. Clearly, the rank 0 is the potential 41. But I have emphasized here, so even in this case, maybe it's not a problem of rank 0. He just gave us clear hints to let us to dive into for the failure processing. But it really saves our time. So more importantly, since the check is runs in parallel on each GPU, it scales very well for the large scale cluster. Okay, so in this way, we just reduce the more than 50 minutes diagnose process to less than 5 minutes. Next, let's look at how we solve the regression problems. So we aggregate this tracing data into 5 metrics. So let me build them up one by one. So first is the training throughput. This is a classical macro metric. So this catches the fail slow problems, but as we said, the blunt regression can't be solved by this matrix. So we need more. So next, 2 kernel level macro metrics, flops and the bandwidth. So flops tell us whether computation kernel actually hit the peak. If the input is big, but the flops is known, it means the kernel is unhappy. Bandwidth it tells us the same stories for communication. So those catch kernel level regression, like backend migration case, we will see in the case 2. So the first one, we call it issue latency distribution. So I think this is one of our key contributions in this work. So issue latency is the gap between when the CPU issues a kernel and when the GPU actually start to run it. So in a healthy job, so the GPU keep busy. So while there will be more idle GPU time in an unhealthy job. So let's look at the figure, the 4.1 example. So the Python runtime kick off a garbage collection in rank 1, and it delays the communication kernel. So it's end up with some interesting results. So you can see there will be shorter issue latency in the unhealthy job than the healthy job, because in healthy job, the GPU is busy, but in unhealthy job, GPU is idle. So the kernel will be executed more faster. The last one, we have the avoid percentage. Because actually, what's our experience like, we can't really understand, get all the details at the first place about GPU. So we have this one. It means this covers everything our tracer doesn't directly instrument. Namely, for example, the inter-step CPU operations and what we can and what we call mirror GPU kernels, like elements-wise activations. So on the timeline, this show up as empty slots gap where low critical kernel is running. So we aggregate the total gap times as a percentage of the step. So the void percentage is back. Something is leaking time outside our instrumented scope. So now let's look at the evaluation. So first question is, Does running Flare in production actually cost anything? Pretty much no. So you can see the figure. Latency overhead is just average about 0.43% across 4 backends on the 1025 H800 GPUs, essentially noisy. So memory is also tiny. A real Llama 20B runs on 1536 H8000s. So we generate 1.5 megabytes of logs per GPUs, compared to the PyTorch built-in profile is 5.5 gigabytes per step. So let's look at the regression. So here is the issue latency CDF. So the curve visualization for regression detection is, so here is roughly linear, dominated by the connective operators. But the unhealthy cases looks different and give the steepest CDF. So we have tested Flare on a 6,000 GPU cluster. So there are 113 real-world training jobs submitted in 1 week. The Flare has labeled 11 jobs with regression flag. 9 of them are true, but the 4 are false. Okay, so let's have a conclusion. So at first, we are using plug and play tracing, so there is no backend source changes. Also, we are targeting some challenging problems like regression and hung errors. So third, we have deployed, I'm using and deployed our Flare in 6,000 scale GPU clusters for 1 year, as it has proved it's a real use in the production environment. Okay, now I will take the questions.